Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. And we lead a semi-charmed kind of life because we are still immersed in the beauty of calculus. This is the last example that we're going to do. So this makes this increasing and decreasing functions, part 4. Let's get down to it. Fully consider this function here, and we need to show that its derivative is equal to this. So whenever you're asked to show that a function, the derivative of a function is equal to something in particular, you should sort of investigate what it looks like, because we could use the product rule or the quotient rule, but this is very much looking like quotient rule because I have some squareds down here in the denominator. Even though it's not exactly this squared, but I think we can see that this is going to factor into x plus 3x minus 1. That's our clue. So since we're using quotient rule, I'm going to start with this. U equals 2x minus 3. And this is my u, right? And this is my v. And du equals 2. And v equals x squared plus 2x minus 3, which means that dv equals 2x plus 2. So using the quotient rule, dy dx is going to equal, I'm not going to say dy dx because it's already labeled as f of x, so I will say f prime of x, the derivative of f of x, is equal to v du. So let's see, v du. So that would be 2 times x squared plus 2x minus 3 minus u, 2x minus 3, dv, 2x plus 2. And that is all over v, so that would be x squared plus 2x minus 3 squared. So let's clean it up, see what happens. So we have 2x squared plus 4x minus 6 minus, now I need parentheses because I need to FOIL this first, 4x squared. 4x minus 6x is going to be minus 2x minus 6 all over, and I got a little bit of work to do with my denominator because they're telling me to make it look like this. Well, let's factor this. So that will indeed factor into x plus 3 times x minus 1, the whole thing still squared. Cleaning up some more, we get 2x squared plus 4x minus 6 minus 4x squared plus 2x plus 6 all over. Okay, and I have two terms, both being squared, so I can write them now just like they want me to as x plus 3 squared multiplied by x minus 1 squared. So at least we have the denominator correct. Let's clean up. Let's see, 2x squared minus 4x squared is negative 2x squared. Okay, 4x and 2x is plus 6x. Oh good, kapow, minus 6 plus 6. Things are looking better, aren't they? So almost there, x plus 3 squared times x minus 1 squared. And now we're going to factor out, let's see, negative 2x, just like they want me to here. So negative 2x, and then that does indeed turn into x minus 3. We did it. So it looks, I forgot the square here. So let's see, let me put the denominator in. So that's x plus 3 squared multiplied by x minus 1 squared. So we did it. Okay. Part A, done. Now, part B, let's take a look-see. Hence, find the intervals where y equals f of x is increasing or decreasing. So we have a new little wrinkle. We need a sign diagram, but what we need to know is that if we have a rational function, we can have changes in increase or decrease not only at not only at points where the derivative is equal to 0, but also where the function is undefined. undefined. Okay? So first of all, where is the function undefined? And you can see where they wanted, why they wanted us to have the derivative look like this with the quotient rule, or we could tell from here. And that is undefined when, let me do my sign diagram. Okay. So it's undefined at, let's see, -3 and 1. So -3 and 1. And so we know they're asymptotes. What we do is we make these dashed. That just reminds us that these are asymptotes. Now I'm going to set the derivative equal to 0. And if a rational function is equal to 0, only its numerator has to be 0. Or that's when, yeah, that's when the rational is 0. So -2x equal to 0 gives me x equal to 0. And x minus 3 equal to 0 gives me x equal to 3. So let me put those in there. They don't have to be evenly spaced. So this is 0, and then, or I mean to scale. And then this is 3. Okay, so let's do our test points. And remember, we're testing the derivative. So we're replacing values in the derivative. And we're going to use the simplest form of the derivative, which is right here. Now, remember, sign diagram, we're just concerned about the sign of the derivative. So let's be smart about this. Let's see if we can take any shortcuts. Well, the denominator, each of these terms is squared. So no matter what we choose, the denominator is always going to be positive. So whether the derivative is positive or negative is going to be solely determined by the numerator. And thank goodness, because that's very, very simple to compute here. So I'm going to start with -4. Let me get rid of this so I have a little bit of scrap work. Well, I can do it up here. -4 for this interval. So -2 times -4, that's a -8, multiplied by a -7. A negative times a negative is a positive. And now I'll try -1. -2 times negative. Oh, wait a second. I messed that up, didn't I? You caught me. I chose -4. -2 times -4 is +8. Multiplied by -4 minus 3 times -7. That is going to be negative. Shame on me. I'm glad I caught that. You were probably screaming at the computer. I hope you were. So now let's try -1. -2 times -1 is a +2 times a -4. That is going to be negative. What about 1/2, I guess, would be easiest. So -2 times 1/2 is a -1 multiplied by +1/2 minus 3. That's going to be a negative whatever, and a negative times a negative is a positive. Now I'm going to test 2. Lots of testing going on. And let's see. Okay, so for 2, -2 times 2 is a -4 multiplied by 2 minus 3 is a -1. A negative times a negative is a positive. And then we'll try +4. -2 times +4 is a -8. And then 4 minus 3 is a +1. So this becomes negative. So there's my sign diagram. Okay. And it's asking where the intervals are increasing or decreasing. So first we will do increasing, and you have to be careful. Okay, let me give you an example. You might want to say, oh, it's increasing, Mr. B, from 0 to 3. Well, you can't say that because the function 1 is not in the domain of the function because it's undefined there. So we would say it's increasing for 0 less than or equal to x less than 1, as well as, notice that it's not equal to 1, 1 less than x, not equal to, less than or equal to 3. And we would say the function is decreasing, same problem here, -infinity less than x less than -3. both less than, because negative infinity is not a number, it's a concept, and its function is undefined at -3. Let's see, also from -3 less than x, less than or equal to 0. And then finally, 3 less than or equal to x less than positive infinity. Okay, so there she is. And let's take a look at her graph. And you can see that the function is indeed increasing from negative infinity. Yes, here. And then we have an asymptote. And then it's decreasing again until we get to 0, where it begins to increase. Yes. And then we have another asymptote. And it's still increasing all the way. Look at this slight little change. The slope becomes 0, and then it becomes negative. So we got our intervals correct. Everything is hunky-dory. Go back and forth and pause if you need to take a quicker look at the graph and the sign diagram to make sure you understand everything there. That is it. I am out.